Okay, so our next speaker is Maria Pomeroy. Maria is a project engineer at Pioneer Technical Services in Butte, Montana, who works on a variety of environmental remediation projects in the state of Montana. In the theme of Dr. McCoy of Star Trek, she would like to remind everyone that she is an engineer, not a statistician, but will do her very best to answer everyone's questions. The name of her talk is XRF to Laboratory Correlation and Regression Analysis, Methodology and Application.
Okay, so our agenda for this presentation, we're just going to go over real quick XRF and ICP, which is the laboratory analytical methods. We'll review quickly what a regression analysis is, and then talk about how a regression analysis facilitates the use of XRF data, and then get into the meat of how to perform a regression analysis and how to apply the regression model once we have one. So to start off, XRF stands for X-ray fluorescence. It comes in the form of, I've heard it called quite often, a gun that shoots an X-ray at a sample, and minimal preparation is required. Sometimes it's helpful to sieve and dry your sample, but a lot of times this can be used in the field directly without a whole lot of sample preparation. So the X-ray excites some atoms in the sample, which sends an X-ray back to the XRF, and the XRF measures the energy of the incoming X-ray to determine the concentration of metals and sometimes other analytes. For this presentation, we're mostly talking about heavy metals. So then the laboratory method that's used most commonly is inductively coupled plasma optical emission spectroscopy, which we're just going to shorten to ICP. So in this instance, we're going to have to, in the case of a solid sample, so soils or that sort of thing, digest the sample in an acid solution, and then that liquid is introduced to a plasma in your laboratory equipment. The samples excite electrons in the plasma, which release different wavelengths of light, and the detector in the instrumentation reads the light with some math and determines the metal's concentration. So as you can see, just talking about this, there are oftentimes some issues with the XRF in reading metals concentrations. The soil, because it's the soil matrix can sometimes cause interference. Other analytes within the sample can cause interference, and you may not get the most accurate sample results. But it is very helpful. So what is a regression analysis? So for the most part, what we're trying to do is fit a mathematical model to a set of data. You get a y, an output value or a predicted value is a function of an input variable, some unknown parameters, and then you usually have an error term. So in this instance, we're trying to fit usually a linear model to our data set. So here we have a scatter plot with our XRF concentrations on the x-axis, our laboratory ICP concentrations on the y-axis. And we're trying to come up with a mathematical model that predicts what, future concentrations could be. So we'll end up with a formula. ICP is equal to some slope times your XRF plus B, your y-intercept. So you usually end up with most regression models, a confidence band where between the upper and lower green dotted lines here, you're 90% sure, 95% sure that your regression line falls in between those two. So for this presentation, I'm going to be discussing, for the most part, the least sum of squares regression method, which is the one you usually learn in a statistics class or a beginning level statistics class. I found out that there are actually quite a few more, but they're not usually covered in just your basic engineering classes. So anyway, so in the least sum of squares method, if we go back to this slide, you've got that error term at the end. For least sum of squares, that is the vertical distance between your regression line and each of your points, which is very important, and we'll discuss here shortly. So for the projects that I've been working on thus far, we've had two general scenarios of when we've done a regression analysis using XRF data. In the first, we've got a mixture of XRF and ICP data that we want to use to model metals concentrations across the site. So we'll use a 3D modeling program to model concentration plumes. In this instance, we use the XRF results where there was insufficient sample size to fill the 4-ounce sample jar that the laboratory required for the ICP analysis. We also use the XRF to sort of help inform where to take samples and where to end them, because we knew that there was a bottom of waste eventually, and so we could use the XRF to inform when we needed, when we could stop taking lab samples. So the purpose of the regression analysis is to adjust the XRF results to better match the ICP results before modeling. For the second scenario, we want to make field decisions about which samples are clean and which samples are waste. We can reduce the number of samples sent for laboratory analysis, which can reduce costs for the project. And then field teams can delineate a removal area in real time. You don't have to wait, the 2 to 3 weeks sometimes for your lab results to come back. So the regression analysis is used then to determine adequate XRF threshold concentrations where you can either, in some cases, over, under remediate an area if you just use the base XRF concentration that you get back. So how to perform a regression analysis, we'll just go through these 8 steps in detail. So step 1, we want to compile the paired data set. So in order to perform a regression analysis, you need to have an XRF result and an ICP result for the same sample. So you definitely want to make sure that when you're taking those samples, sending one to the lab and then analyzing one with the XRF, that they are from the same sample interval, and you've done a pretty good job mixing the samples together so that you've got what you're hoping is you're analyzing the exact same thing or as close as you possibly can get. One thing to keep in mind when you're compiling your paired data set is you want to keep track of which samples are non-detect. Depending on what you're doing, sometimes you want to remove those non-detect sample pairs. The XRF especially, they don't always have the best detection limits, and so sometimes it's better just to take the samples that have non-detect XRF results out of the analysis and just go with your detected results. So the confidence in your regression model is going to be higher with more paired samples. So you want to aim for a minimum of 30 to 40 paired samples, but the more you can get, the better it's going to be. So you can use that to predict. It also will narrow those confidence bands a little bit if you have more data. And yeah, it just makes everything better in the long run, the more samples you have. So step 2, plot the paired data set on a scatter plot. So first off, you want to make sure you actually have something that kind of has a linear relationship. You don't want to end up with something that actually ends up looking like having an exponential relationship, or, there are a lot of different mathematical models you want to use. So in this instance, we're going to just plot those points on a scatter plot and see what they look like. Sometimes, too, you have more than one population in your data set, which means that there's something going on that's changing those analytical results. So this is actually looking at ICP and SPLP results, but in this instance, there's some other factor at play here that's changing things. So you can see you've got 2 different populations in your sample. And you don't want to do a regression analysis on this whole sample set. You want to figure out what that second or sometimes third variable is that's separating these 2 populations and do a regression analysis on each one. So step 3 is to assess the linear relationship of the variables. So here I've got the general formula for the correlation coefficient, often known as R. And so it's just equal to the covariance of x and y divided by the square root of the product of the standard deviation of your y data and the standard deviation of your x data. And so this is one of those variables that It generally ranges from -1 to +1. -1 is a really strong negative relationship, and +1 is a really strong positive relationship. And I have listed here to, an acceptable R value for a linear relationship is 0.7. A good relationship would be greater than 0.83. Just try to, in general, I guess. So step 4 would be to identify outliers, if any, and remove them from your final data set. So this is a newer outlier analysis method called the Bland-Altman outlier analysis. Here we are plotting the product of your XRF and ICP on the x-axis, and then the difference between the XRF and ICP concentrations on the y-axis. And then you've got bands for the upper 95% and lower 95%. And if you have any points that fall quite a ways above or quite a ways below those 95% bands, you can usually take those out and identify them as outliers and remove them before you conduct your final regression analysis. And it's always a good idea to go back to your initial scatter plot, look at those outliers, and make sure that it does make sense for them to be outliers before you take them out of your final data set. And then also a good idea, just relook at that correlation coefficient R, make sure nothing weird happened and your correlation coefficient didn't decrease, because that would indicate that you have less of a linear relationship than you did before. So step 5 is to assign the variables to the x and y axes. And this is particularly important if you're using the least sum of squares method. So just going back to a review of how the method works, least sum of squares, you are minimizing the vertical distance between each point and that regression line. And that's how the math works out when you're calculating the formula to get that slope and y-intercept. So this means, therefore, that the method is not invariant. So if you set your XRF as the x variable and your ICP as a y variable, you'll get a formula ICP is equal to mx plus b. If you set your XRF variable as your y variable and ICP as your x variable, again, you get two slopes. If they have a perfect linear relationship, then if you take the inverse of those formulas, then your first slope should be equal to 1 over the second slope. But because we're looking at minimizing different distances between the points in the regression line, you're going to get different slopes and y-intercepts, especially if your linear relationship isn't a perfect one, which in the case of XRF to ICP data, I don't think I've ever seen anything near close to 1. So if you're looking at just like visualizing how the two methods or how the method is not invariant, in the one instance, you're measuring the vertical distance. If you switch those variables but plotted them on the same graph, you'd actually be minimizing the horizontal distance. So different lines, very important. Before you start setting up your regression analysis, you decide which one you want to put on the x and which one you want to put on the y when you're creating that regression line. So two kind of important questions to ask yourself is, what will the regression analysis be used for? So you want to assign the variables to match the regression format where x is the input variable and y is the output variable. And then ask yourself which variable will be predicted, and assign the predicted variable to the y-axis. So for the two scenarios I described before, where we're modeling a mix of XRF and ICP data together, or we're using the XRF to make field decisions, the XRF was the input variable, and we set the ICP as the output variable. Generally speaking, our ICP was our predicted variable. We're going to be going out and collecting XRF data. We want to know what the ICP concentration would be since we're not necessarily going to be measuring it. So step 6 is complete the regression analysis. This is the easy part. This is where you let the computer do the work. I mean, if you want, you can do it by hand. the math isn't too terribly difficult. But some of the statistical tools available to you, Excel's data analysis tool pack, which comes with Excel, is pretty easy to use. There are other Excel add-ins you can download online. If you want to get a little fancier, you can go with R, which is a really robust statistical software that's free. And then there's MATLAB. And if you still want to keep looking, I put a link in here for Wikipedia. It has a long, very long list of statistical software available. And then going back to regression methods. So there are other regression methods out there. So here we're going to talk about least sum of squares. There's orthogonal regression. In this case, instead of minimizing the vertical distance between points, you're minimizing the perpendicular distance between points to the line. There's Deming regression, passing Bablock method, which I've learned a lot about recently. Passing Bablock, you actually calculate the slope between every two possible points in your data set and find the median slope, and that's your regression line. And then principal component regression was really complicated, and I'm sorry I don't really have that much information about that one. And then in the end, if you decide to use a different method or even using least sum of squares, read the fine print, aka the assumptions, before selecting any method. Every method that you use, there's some base assumptions that definitely will make a difference on the slope and y-intercept you get, and can have some interesting implications for your final regression model. So step 7, we're going to assess the fit of the regression model. So for the least sum of squares method, this is the coefficient of determination. Now, if you pick a different regression method, so like passing Bablock or the Deming regression, they have their own methods for assessing the fit of the model. So R squared isn't going to be applicable to those other methods. But for least sum of squares, you're measuring the amount of variance between the predicted y values and the regression, you're measuring the variance between the actual y data and your predicted y data, and dividing that by your the variance in your y data set. And a value of 1 indicates that you've got a perfect regression model. Every point lines up exactly on that regression line. If you end up with an R squared value of less than 1, which is possible, it means you've got more variance between your model, or the model creates more variance in the data than exists in your Y data set, and that's not a good thing. So if that happens, I suggest you start over because something went terribly wrong. Again, I've got some recommended acceptable R squared values of 0.5, and a good R squared value is greater than 0.7. So step 8, we're going to apply the regression model to the XRF data. And so we're going back to those 2 initial scenarios that I discussed before. So for scenario 1, where we've got a mix of XRF and ICP data that we want to use to model metals concentrations across the site, you get your regression line, which runs through the middle, or generally through the middle of the data. We're going to go ahead and use, to be more conservative, we'll use the upper 95% confidence in the slope and y-intercept line. And this is that confidence band. Your regression line should fall, or you're 95% sure the regression line falls somewhere between the upper and lower green dashed lines shown here. So using the upper 95% line, you're being a little bit more conservative on when you're importing that XRF data into the data set and modeling it. So for scenario 2, when we're making field decisions about which samples are clean and which samples are waste, there are several considerations you want to keep in mind. So in this instance, we want to reduce the occurrence of false negatives and false positives. So in a false negative situation, the X, which is, if you show it on a scatter plot, it's that yellow square on the left. So in this instance, your XRF is showing that the sample is clean. But if you sent it off to the lab, it would actually be waste. And so in this instance, you could potentially under-remediate a site. You could be taking soil samples from a particular area, and you would miss a spot. You also want to reduce false positives, and this is more of a cost savings thing. In this instance, your XRF is showing that the sample is waste, but if you send it off the lab, it would actually be clean. So if you get false positives, you're going to end up over remediating a site and cleaning up someplace that you don't necessarily have to. So in between this, I've got the green sort of confirmation zone. In here, you're not 100% sure whether the XRF concentration is showing that it's waste or it's clean. So you can send this subset of samples off to the lab just to confirm whether they're waste or clean, just double check. So to determine those, what we're trying to determine is that dashed green line that bans that confirmation section. So to calculate that, we're going to calculate what are the prediction interval lines. And so this is, for instance, the red dashed lines here, you're 95% sure that future ICP samples will fall between the top and bottom line. And this is different from that confidence on the slope and y-intercept line, in that we are specifically looking at the distribution of points around the regression line. And so with the least sum of squares method, typically your residuals are going to be normally distributed. And since you know that they're normally distributed, you can use that mathematical distribution to predict future values. So you can say, okay, I want to be 95% sure I don't have any false negatives. And I want to be, I'm not quite as concerned about the false positives, so we're going to do 70% on that. So where, if you were to show this on a graph, then your XRF concentration confirmation interval would be the intersection between your upper and lower prediction interval lines, depending on your confidence that you want to set in preventing false negatives and false positives. And you can use this when we were talking about like in the field using the XRF to determine, what's waste and what's not. If you can, do some, or if you don't want to do the confirmation section, you don't want to send any samples off to the lab at a certain point. Say you've gotten your waste pretty well delineated, you want to send the field teams out to just do a little bit more confirmation sampling, then you could potentially use that lower XRF threshold value to say, okay, in these areas we know we're getting closer towards the clean area, we're not super concerned about over remediating, so let's just use that lower XRF threshold concentration to say this is waste, and so we're going to remediate here. So that is the end of that. I'm sorry that was so fast.